So coming to the applications of jet transformations. So first application directly we discuss about the first point. First is the system function. How we can calculate the system transfer function. System function or the another name for the system transfer function, or simply it is also called as sometimes system function also. So nothing but in the DTFT, system function or signal function is nothing but in frequency domain is h of e power j omega, which is equal to the y of e power j omega divided by x of e power j omega. In similar way, in the jet transformation also, the system transfer is nothing but a y of z by x of z. How we can calculate that one? That's the main thing here. So all of you know this one. For an LTI system, generally the basic points I'll discuss it here. So for an LTI discrete time system, the difference equation, the LCCDA, linear constant coefficient difference equation is given by all of you know this one. The system present output is depends upon the parameters like present input, past inputs as well as the past output. So that is nothing but a y of n is equal to summation k is equal to 1 to n ak into y of n minus k, nothing but a past outputs plus present input. N is equal to 0 to m bk into x of n minus k. This is the present input. At n is equal to 0, you can get the present input. At n is equal to 1 to m, you can get the past inputs. So present output is nothing but a y of n here, and past outputs are nothing but a k is equal to 1 to n here. So from this one, apply the jet transformations on both sides here. We get that system transfer function here. Apply the jet transformations on both sides here. The transformation on both sides. So first y of z is equal to summation. Jet transformation is applied only for signals, not for other values. So that k is equal to 1 to n ak into what is the jet transformation of y of n minus k according to the time shifting property, which is equal to the y of z into z power minus k. Y of z into z power minus k plus summation k is equal to 0 to m bk into x of z into same according to the time shifting property x of j into z power minus k. So from this one we can common the y of z, because the system transfer function is always equal to the output by input. So that which is equal to the 1 minus summation k is equal to 1 to n ak into z power minus k is equal to summation k is equal to 0 to m into bk into z power minus k into x of z. So from this one, the system transfer function is always equal to, so earlier in the first unit already linear constant coefficient difference equation, we discussed about how the relationship between the input and output which was described by the difference equation. What is that difference equation? So for this one already discussed here. So where in this case past outputs is mentioned by the minus here. So that which is equal to the plus. So from this one, the system function or the system transfer function. From this one, system function is always equal to the, which is denoted by the h of z, which is equal to the ratio between the y of z and to x of z. X of z, so which is equal to the summation k is equal to 0 to m into bk into z power minus k divided by 1 plus summation k is equal to 1 to n into ak into z power minus k. So which is also mentioned as n of z by d of z. N of z by d of z. So this is about the system transfer function. How we can calculate the system transfer function by using the jet transformation? This is the procedure. If for a given difference equation, just we apply the Z transformation on both sides, and from that one y of z, we can calculate the ratio of y of z to x of z, that is called as the system transfer function h of z. Suppose here one important point is, if input x of n is equal to, if input x of n is equal to delta of n, that is its z transformation x of z is equal to delta of z, which is equal to the 1. So what is that one? Then the system transfer function h of z is equal to y of z. So from this one we can get the, after applying the inverse z transformation here, after applying inverse z transformation, after applying inverse z transformation, then the response is called, then the response is called h of n, that is nothing but h of n is denoted by impulse response. Impulse response, because here the input is x of n is equal to delta of n, so its a corresponding response is called as impulse response. Suppose if we apply the x of n is equal to u of n, suppose if we apply if x of n is equal to u of n, so that u of n is nothing but a step signal, so the corresponding system response is called as step response. So this is about the concept of the system function and how we can calculate the system function. From that system function, how we can calculate the responses, impulse response and step response. Impulse response and step response. So this is about the first application of the Z transformation. So one by one we discussed here. Continuously you can go for one after another. Okay. So next case is a pole zero plot. Pole zero plot. So first application is nothing but a how to find the system transfer function. Second one is the pole zero plot. After getting the fraction system transfer function, which is in the form of n of z by d of z, then we can calculate the poles and zeros. I think all of you know this one. All of you know this one. The system function, the discrete time system, the system function h of z is equal to, always it is the fraction like n of z by d of z. So very simply you can say that, here the poles of the system function, the poles of the system function is always equal to the h of z. The poles of the system function h of z are the z are the values of z for which h of z is equal to infinity. The first case is the poles of the system function. Clearly observe it, my statement. The poles of the system function, the poles of the system function h of z, for which h of z nothing but a h of z are the values of z, for which h of z is equal to infinity. For which h of z is equal to infinity. When h of z is equal to infinity, when h of z is equal to infinity, denominator d of z is equal to 0. If the d of z is equal to 0, anything by 0 is always equal to infinity. Then that is, if the denominator of the system function d of z is equal to 0, then find the values of z. All those values of z are nothing but a poles of the system function. If it is a second order system function, 2 poles are existed. If it is a third order, 3 poles are existed. So that is a d of z is equal to 0. Next, second one, same statement. Poles, after the calculating the poles, then the zeros of the system function. Clearly observe it. The zeros of the system function h of z are the values of z are the values of z are the values of z for which are the values of z for which h of z is equal to 0. When the h of z is equal to 0, if the numerator part is equal to 0. So nothing but that is if the numerator n of z of the system function is equal to 0. So just finally you can conclude that how we can identify the or how we calculate the poles and zeros of the system is always if the numerator is equal to 0, we can get the zeros of the system. If the denominator is equal to 0, we can get the poles of the system. How we can plot the poles and zeros on the z plane? The plotting of the poles and zeros are like this one. So it is nothing but a real part of z. It is minus real part of z and which is equal to the imaginary part of z and which is nothing but a minus imaginary part of z. I think all of you know this one. Poles are always mentioned by the cross mark. Poles are always mentioned by the cross marks. These are the poles mark. The poles may be existed at any time, at any place in the pole zero plot, and the zeros of the system function is always mentioned by the zero, like nothing but a circle, like this one. So in this one, so this is nothing but a poles representation. This is the zeros representation. So this is the pole zero plot. How after finding the poles and zeros of the system, we can plot the poles and zeros on the pole zero plot. So these are the two applications of the Z transformation. One is a system transfer function. After calculating the system transfer function, then we can calculate the poles and zeros and then plot the poles and zeros. Based on the pole's location in the Z plane, we decide whether the system is causal or stable or causal and stable. So that is the next application of the Z transformation. That is the third application is causality and stability of the LTI system. The main intention or the main objective of the why we go for the Z transformation means this is the main important one of the important point, causality and stability of the LTI system. Actually, in general case, in general way, we can't judge the whether the system is exactly causal or not, whether the system is exactly stable or not. But by using this Z transformation technique, you can easily say that whether the system is causal or anti-causal, whether the system is stable or unstable, or whether the system is causal and stable also. Yes, are all of you following? So these are the first cases, system transfer function or system function. First we go for LCCDE, linear constant coefficient difference equation, or which represents or which describes the relationship between the input and output parameters. So from that one, first we calculate the system transfer function. After that, identify the poles and zeros of the system. Then we will go for causality and stability of the system. So now we can go for the one or two points related to the causal and stable. All of you know this one. The stability of the system is always is nothing but it satisfies the Bibo principle, bounded input and bounded output. For a given bounded input, the system produces always bounded output, then it is called as stable system. Similarly, for causal means it's the system impulse response h of n is equal to 0 for n less than 0. Nothing but the system is defined for only right sided. Can anyone say that what is the ROC of the causal signal? What is the ROC for the causal signal? Anyone? What is the ROC of the causal signal? And we are clearly mentioned ma. What is the ROC? Region of convergence for the causal signals is always greater than, and it is always less than for anti-causal signal with respect to the value. Okay. So first we start with that statement ma. Okay. Yes, all of you write down. A system is said to be causal. It's the most important ma. A system is said to be causal The system is said to be causal. Its ROC, its ROC is exterior to the circle. Already this property is discussed in the ROC property. Exterior to the circle with radius r, with radius r, that is mod z greater than r. When we are solving the problems in the class also, we discuss the same point. If it is a greater than r, that is causal. If it is a less than r, that is anti-causal. So based on the ROC only, you can say that whether the system is causal and non-causal or anti-causal. The system equation for the causal system is, so first we go for the causal. The system equation for causal systems, the system equation for causal system is, what is the impulse response of the causal system? Impulse response of the causal system is h of n is equal to 0 for n less than 0, that is for causal system impulse response. So from this one, the system transfer function h of z is equal to summation n is equal to 0 to infinity h of n into z power minus n. This is the system equation for the causal sequence or causal system transfer function. Apply the modulo operation on both sides. Apply the modulo operations. That is, modulus of h of z is always equal to modulus of summation n is equal to 0 to infinity h of n into z power minus n. So according to the mathematical inequality, I think all of you know this one. Mod AB is always less than or equal to mod A into mod B. So according to that concept, that h of z is less than or equal to summation n is equal to 0 to infinity into h of n into z power. This is the modulus operation, modulus of A into modulus of B. So clearly observe it. For stable system, so that for stable system, what is the condition? This is the bounded output. Okay, and this is the input. This input is also bounded input. Then what about this term? Z power minus 1. When the system is said to be stable means, that mod z is, or z power minus 1 is always equal to the 1 only. If it is always equal to 1, automatically the system produces the bounded output for a given bounded input, so that the system is said to be stable system. That is, simple point means, that is z power minus 1. This total component, this modulus of z power minus n is always equal to 1. That is nothing but we can evaluate on unit circle. You can evaluate on the unit circle. So for a stable system, its impulse response for a stable system, so condition is, for a stable system, z power minus n, modulus of z power of minus n is always equal to 1. That is, that is the value of ROC for the stable system, that ROC is always less than 1. The ROC for the stable systems is always 1, less than 1. So clearly observe it. Now we can just combine the causal and stable conditions. So you can conclude the points here. For causal systems, a simple logic. For causal systems, what about the ROC here? Mod Z greater than R. Then what about the for stable systems? It will be evaluated on the unit circle. For stable system, the ROC must be mod Z less than 1. So for causal and stable system, if any system is said to be causal and stable system, what about the ROC? That ROC is always, so here mod Z greater than R and less than 1. So if any system is said to be causal and stable system, its ROC must be evaluated on the unit circle. ROC is greater than the radius, greater than the circle with the radius R, where that R is equal to 1. Okay, this is about the causality and stable system. So finally just we can conclude that if for any causal and stable systems, for any causal and stable system, all poles must inside the circle with radius R is equal to 1. Why? If the ROC is greater than 1 for any system, ROC does not contain the any poles. So that condition is satisfied. That property is also satisfied. So automatically it will be evaluated on the unit circle also, so that for a causal and stable systems, the ROC must be greater than the R with radius R is equal to 1, and all the poles that must be inside the unit circle, nothing but a inside the circle with radius R is equal to 1. So this is the ROC of this causal and stable system, and which is a radius circle with radius R, and whatever the poles are having this system function, that must be inside the unit circle or inside the circle with radius R, because ROC does not contain the any poles. That is already universal rule. According to the ROC properties, ROC does not contain the any poles. If any one pole is located on outside the circle, automatically that must be unstable. It is nothing but a Laplace transform. All the poles that must be left side of the S plane for stable and causal system. Suppose if any one pole is located at right side of the S plane, the system is said to be unstable in case of the Laplace transform. Similarly, here also same thing. If all the poles are located must and should in inside the unit circle, then the system is said to be stable and causal. Suppose if any one pole is located in the ROC, automatically that must be unstable system. Suppose if the poles are located on the unit circle, marginally stable system. So this is about the conclusion for the causal and stable systems. This is about the third application. So first application is system transfer function. Second application is pole zero plot. and based on the location of the poles and zeros, we can conclude that whether the system is stable or not. Clearly mentioned ma, link one by one having the application is link. First is system transfer function h of z, then poles and zeros, and plot the poles and zeros on the pole zero plot. And if all the poles are inside the unit circle, then it is causal and stable. And here one more thing clearly observe it. Based on this conclusion, based on this concept, we can conclude that whatever the poles are having the system, all the poles having the values are less than 1. If any one pole is greater than 1, automatically the system is unstable. Okay, this is about the concept of the causal and stable systems. The fourth application is, already we discussed about the relation between the jet transforms and DTFT. It is a general concept. Already we completed this one. Just I will give the relation between the jet transformations and DTFT, because we are having the various transformation. So all those transformations are most important. So how we can convert one transform to another transform, that is a very easy here. So first, jet transformation definition: x of z is equal to summation n is equal to minus infinity to infinity x of n into z power minus n, x of n into z power minus n. And similarly for frequency response DTFT, x of e power j omega is equal to summation n is equal to minus infinity to x of n into e power minus j omega n. So this is the jet transformation of the sequence x of n. This is the DTFT of the sequence x of n. Discrete time Fourier transform. Just compare the both the equations, ma. Compare the above equations. It's a very simple, ma. So x of e power j omega is equal to x of z, where at z is equal to e power plus j omega. So this is the relationship between the discrete time Fourier transform and jet transformations. So if you are having any doubt, please ask me. Till now, these are the applications of the jet transformations. So all of you please go through your notebooks. So first we calculate the first for a given difference equation LCCDE. We calculate the transfer function by using the jet transformations or by applying the jet transformations here. After calculating the system function h of z is equal to y of z by x of z, then plot the location of the poles and zeros on the z plane. By the concept is a denominator d of z is equal to 0, we get the poles values of the poles. If numerator n of z is equal to 0, we obtain the values of the zeros. After poles and zeros location on the z plane, so based on that location of the poles and zeros, we decide that either the system is causal and stable or only causal or only stable. This is the concept. Okay, so you can take an example problem here. All of you just note down the problem, example problem. If you solve the problem clearly, definitely you get the clarification on these all applications. So write down, determine the system function, comma, impulse response IR, comma, pole zero locations, frequency response, nothing but a x of e power j omega, frequency response, and check the stability and check the causality and stability. Check the causality and stability. Stability of the system described by described by difference equation LCCDE of the system described by LCCDE difference equation y of n minus 3 by 4 into y of n minus 1 plus 1 by 8 into y of n minus 2 is equal to x of n minus x of n minus 1 for n greater than or equal to 0. What is the meaning of n greater than or equal to 0? Causal signal, causal system. Okay. So this is the equation one. So how you can solve this one? I think all of you following this problem. So with the help of this problem, clearly we get the idea, complete idea about the applications of the jet transformations. Okay. So first given equation. In the examination also you can follow the same procedures, then we can get the good marks. For the given equation, y of n minus 3 by 4 into y of n minus 1 plus 1 by 8 into y of n minus 2 is equal to x of n plus x of n minus 1. So first, what is the first step? What is the first step? Anyone? I will give already mic permissions, ma. If you unmute and give the answer, no problem. So after applying the jet transformations on both sides, y of n is nothing but y of z minus 3 by 4 into y of z into z inverse plus 1 by 8 into y of z into z power minus 2 is equal to x of z plus x of z into z power minus 1. X of z into z power minus 1. So first common for the y of z, 1 minus 3 by 4 into z inverse plus 1 by 8 into z power minus 2 is equal to, and right side you can common for x of z, 1 plus z inverse. 1 plus z inverse. So I think all of you know this one. The system function. What is the system function? H of z is equal to, what is the definition of h of z? Y of z by x of z. So y of nothing but a 1 plus z inverse divided by, sorry ma, x of n plus x of n minus 1. Okay. So 1 plus z inverse divided by 1 minus 3 by 4 into z inverse plus 1 by 8 into z power minus 2. So this is about the system transfer function h of z using jet transformations. Next is impulse response. So what is the impulse response? Inverse jet transformation of h of z. So impulse response is nothing but a h of n. So h of n is nothing but a inverse jet transformation of h of n. Inverse jet transformation. So for now coming to the h of n is equal to inverse jet transformation of h of z. So first we simplify the h of z in another form. So h of z is equal to 1 plus z inverse, 1 plus or 1 minus? Okay, 1 plus. So 1 plus z inverse divided by 1 minus 3 by 4 into z inverse plus 1 by 8 into z power minus 2. First, for calculating the poles of the system function, we just convert into the positive powers of z. So nothing but a z power minus 2. If you multiply with the z power minus 2, so z square plus z divided by z square minus 3 by 4 into z plus 1 by 8. So you can common the z power minus 2 for both numerator as well as the denominator. Then it will be changed to the form to the positive powers of z. So which is equal to the z square plus z divided by z square minus 3 by 4 into z plus 1 by 8. So now in the partial fraction method, you can apply the partial fraction method. So I think all of you know the apply the partial fraction method here. Apply the partial fraction method. That is h of z divided by z is equal to z plus 1 divided by z square minus 3 by 4 into z plus 1 by 8. So I think all of you know the roots here. 1 by 8, nothing but a 3 by 4 is the 1 and 1 by 4 is 1 by 2. Sorry, 1 by 4 and 1 by 2 are the roots for this 1 by 8. So for the denominator, the roots are z plus 1 divided by z minus 1 by 4 into z minus 1 by 2. So this is about the concept of the yes, my roots are okay or not okay. Clearly give the answers now. Z square minus 1 by 4 z minus 1 by 2 z. So minus of 1 by 4 plus 1 by 2. 6 by 8, 3 by 4. Okay, right. Okay, 1 by 4 and 1 by 2. So apply the partial fractions method here. H of z by z is equal to z plus 1 divided by z minus 1 by 4 into z minus 1 by 2 is equal to a by z minus 1 by 4 plus b by z minus 1 by 2. So after calculating this one here, calculate the a value here. So first a value is equal to residue. Apply the either residue method also, no problem. So z minus 1 by 4 into z plus 1 divided by z minus 1 by 4 into z minus 1 by 2 at z is equal to 1 by 4. So z minus 1 by 4, 1 by 4 get cancelled, and final answer is 1 by 4 plus 1 is numerator is 5 by 4 and denominator is 1 by 4 minus 1 by 2, nothing but a minus 1 by 2. So what is the final answer is minus 10 by 4 is the a value, and similarly for b value is equal to z minus 1 by 2 into z plus 1 divided by z minus 1 by 4 into z minus 1 by 2. So 1 by 2, z minus 1 by 2, 1 by 2 get cancelled, at z is equal to 1 by 2. 1 by 2 plus 1 is 3 by 2 divided by 1 by 2 minus 1 by 4, 1 by 2. So answer is 2 get cancelled. So answer is 3. Answer is 3. So this is about the concept of the so A value and B value. So that from this one h of z by z is equal to, so final answer h of z by z is equal to a by z minus 1 by 4. What is the value of a? Minus 10 by 4. So that minus 10 by 4 into z minus 1 by 4 plus 2 by, sorry, z minus 1 by 2. 2 or 3? 3. So which is equal to the 3 by. So again h of z is equal to, now we can apply the inverse transformation. Minus 10 by 4 into z minus 1 by 4 z by plus 3 into z by z minus 1 by 2. So I think all of you know this one. Now we can apply the inverse z transformation here. H of n is equal to minus 10 by 4 into, which is in the form of z by z minus a. Nothing but a 1 by 4 into whole power of n into u of n plus 3 into 1 by 2 into whole power of n into u of n. So this is the system impulse response h of n. System impulse response h of n. Next, third application is a pole zero plot. It's a very simple pole zero plot. So how you can plot the poles and zeros? So for this one, first we go for h of z here. H of z is equal to, what is h of z here? Z square plus z divided by z square minus 3 by 4 into z plus 1 by 8. So which is equal to the z square plus z divided by z square plus divided by z square minus 3 by 4 into z plus 1 by 8. So which is equal to the z into z plus 1 divided by z minus 1 by 4 into z minus 1 by 2. So which is in the form of numerator by denominator. So I think all of you know this one. How to get the zeros of the system? Nothing but it is the values of h of z. For h of z is equal to 0. When it is equal to 0, numerator is equal to 0. If n of z is equal to 0, we obtain the zeros. We obtain the zeros of the system. We obtain the zeros of the system. So that is, what is the numerator? Z into z plus 1 is equal to 0. So nothing that from this one, two zeros are getting. Z1 is equal to 0 and Z2 is equal to minus 1. Next, what about the poles? Poles are nothing but these are the values of z for which h of z is equal to infinity. When it is infinity, if d of z is equal to 0, at that time we obtain the poles of the system function. At that time we obtain the poles of the system. So nothing but what is the denominator here? Z minus 1 by 4 into z minus 1 by 2 is equal to 0. So poles are denoted by the P1. So P1 is equal to 1 by 4 and P2 is equal to 1 by 2. Simple is z minus 1 by 4 is equal to 0. Z minus 1 by 2 is equal to 0. So from this one, z is equal to 1 by 4, z is equal to 1 by 2. Okay, na? Suppose here z plus 1 by 4 is there. So at that time pole is equal to minus 1 by 4. Okay. So this is so these are the poles. So now we can just plot the poles and zero plot. So based on this we can conclude that it is a either it is the causal and stable system. Already it is a causal. Why? Because it is the reason is only n greater than or equal to 0. Already in the problem they mentioned clearly. So now coming to the pole zero plot here. First we can plot the poles. poles P1, what is the value of P1? 1 by 4, it is the 0, so that so 1 by 4 and 1 by 2. So one pole is located at 1 by 4, another pole is located at 1 by 2. Okay, and the zeros are denoted by the circle, so that the Z1 is equal to 0 and Z2 is equal to -1. So this is the unit circle ma. So poles and zeros are plotted. Zeros does not affect the stability of the system. Only poles are affected the stability of the system. And what about the ROC of this system function? It is a mod z greater than 1. Mod z greater than 1 by 2 is the ROC. So that ROC does not contain the any poles here. So the property of the ROC is also proved, and so that the system is, either the system is here is causal. Why? Because it is causal. ROC is greater than 1 by 2 and stable. Why it is stable? All the poles are must be inside the unit circle. So this is about the, based on the pole zero plot, we can check or we can verify whether the system is stable or not stable. So this is the applications of the jet transformation. So in the problem, the system function is over, impulse response is over, pole zero locations is over, and checking the causality and stability of the system is also over. Only the left out topic is here is frequency response. For this frequency response, we go for relation between the DTFT and jet transformation. So x of e power j omega is nothing but a frequency response. Always omega is mentioned. So nothing but which is equal to the x of z at z is equal to e power j omega. So here also same, h of e power j omega. The frequency response of the system is always equal to the h of z at z is equal to e power j omega. So what is the value of h of z? What is the value of h of z here? 1 plus z inverse divided by 1 minus 3 by 4 into z inverse plus 1 by 8 into z inverse, where at z is equal to e power j omega. Just we can substitute, you can get the frequency response. H of e power j omega is equal to 1 plus e power minus j omega divided by 1 minus 3 by 4 e power minus j omega plus 1 by 8 into e power of minus j omega. As per z inverse or z power minus 2. A small mistake here. Z power minus 2. So nothing but a 2j omega. So this is about the frequency response of the discrete time LTI systems. So these are the applications of the jet transformation. How we can calculate the how we can evaluate the applications of the jet transformations with the help of the function. So now the applications, system transfer function or system function. For a given LCCDE, we can apply the jet transformations on both sides. Then you can get the system transfer function h of z is equal to y of z by x of z. Then pole zero plot. If the numerator is equal to 0, you can get the zeros of the system function. If the denominator is equal to 0, you can get the poles of the system function. After plotting the poles and zeros, check whether the system is causal or non-causal, or stable or unstable. So if the poles are outside the if the poles are inside the unit circle, then the system is said to be stable. If the ROC is exterior to the circle, then it is called as a causal signal. So for our problem, it is a system is causal and stable system. Next, how to get the frequency response x of e power j omega from the x of z? Simply in place of z, we can substitute e power j omega. So we will discuss one problem also. So if you are having any doubt, please ask me till now. So there is an interactive session. If you are having any doubt, please ask me, or you can ping me, no problem. So tomorrow we'll discuss about the how to solve the differential equations by using jet transformations. Already we are completed, ma. This is the This is the difference equation. How to solve this difference equation? By using this one. Actually, it is a generalized time shifting property. Suppose for whenever the system initial conditions are provided, then you can go for one-sided jet transformations. So that concept will be discussed in the tomorrow class. So tomorrow we'll discuss about the solution of LCCDE as well as the realization of the discrete time systems for IAR as well as the FIR systems. Okay. So I hope that all of you understanding the complete applications of the jet transformations. Okay. If you are having any doubt at any time, please ask me. No problem.